The velocity triangle of Pelton wheel turbine is very important for understanding of design aspects of Pelton wheel. In this video, you will see how the velocity triangle is constructed in the simplest way. So let's begin the discussion and then see how velocity triangle is drawn. So before constructing the velocity triangle, let us understand the velocity terms. So inlet mean bucket velocity is u2. Inlet mean relative velocity is v2. Inlet mean absolute velocity is c2. Inlet mean whirl velocity or tangential velocity is cw2. Inlet mean axial velocity is ca2. Outlet mean bucket velocity is u3. Outlet mean relative velocity is v3. Outlet mean absolute velocity is c3. Outlet mean whirl velocity is cw3. Outlet mean axial velocity is ca3. Outlet mean blade angle with respect to axis of rotation or axial is beta 3. Outlet mean absolute velocity angle with respect to axial is theta 3. So units of all the above velocity are in meter per second and unit of blade angle is in degree. This is the runner. So mean diameter of runner is dm. So velocity triangle is drawn at this middle of the mean diameter of the runner. That is dm is a bucket or runner mean diameter in millimeter, n is the speed of the bucket in rpm. This is the direction rotation of the bucket, and fluid is striking at the center. It is deflected on both sides, but for drawing the velocity triangle we can take any one side as an outlet velocity triangle. Inlet mean absolute velocity c2. So draw the inlet mean absolute velocity in the direction of rotation of bucket. Inlet mean absolute velocity depends on water head available. Higher the head, inlet mean velocity will be also higher. So this is C2. It is drawn. Now inlet mean bucket velocity U2. Inlet mean bucket velocity in this is draw in inlet mean bucket velocity in the same direction as the direction of bucket, and it depends on the speed and bucket mean diameter of a runner, which is expressed as u2 is equal to pi dm n upon 60 into 1000 meter per second. So this is u2 and this is u2 and this is c2 in the same direction as the direction of rotation of bucket. Inlet mean relative velocity v2. Draw the inlet mean relative velocity in the same direction as the direction of rotation of the bucket. So same direction. And inlet mean relative velocity is equal to inlet mean absolute velocity minus inlet mean bucket velocity. So V2 is equal to C2 minus U2. You can see V2 is equal to C2 minus U2. Now inlet mean whirl velocity CW2. Tangential component of inlet mean absolute velocity is called the inlet mean whirl velocity, and inlet mean whirl velocity is equal to inlet mean absolute velocity. So you can see CW2 is equal to C2. C2 is equal to CW2. Inlet mean axial velocity CA2. Axial component of inlet mean absolute velocity is called inlet mean axial velocity, but there is no component of axial. So axial mean inlet mean axial velocity is 0. So CA2 is 0. Now outlet mean relative velocity V3. Draw the outlet mean relative velocity in the direction of outlet mean bucket angle, that is beta 3. As there is a pure impulse, and so the outlet mean relative velocity will be equal to inlet mean relative velocity. So V3 is equal to V2. Considering the friction losses, we can write V3 is equal to V2 because this is a pure impulse. Now outlet mean bucket velocity. Draw the outlet mean bucket velocity in the same direction as the direction of the bucket. So it is drawn in this direction, and it depends on again speed and the bucket mean diameter of runner. So which is expressed u3 is equal to pi dm n upon 61,000. So outlet mean bucket velocity is same as inlet mean bucket velocity. So u3 is equal to u2. You can see u3 is equal to u2. Sorry, u2 is equal to u3. Both are same. So it is drawn like this. So these two are same. Outlet mean absolute velocity. Join the starting point of outlet mean relative velocity, that is this, to the end point of outlet mean bucket velocity, this. So you have to connect this. This will be outlet mean absolute velocity, that is C3. Outlet mean whirl velocity. The tangential component of outlet mean absolute velocity is called the outlet mean whirl velocity. So CW3 can be positive or negative. So this can be positive if this is this direction, negative if it is in this direction. So if negative, it will be opposite direction to the wheel rotation. If positive, it will be the same direction as the wheel rotation. So this is positive. If it is coming here, this is negative. The best design is to minimize the value of CW3. Main intention is we to minimize CW3 as a good design. Outlet mean axial velocity CA3. Axial component of outlet mean absolute velocity is called the outlet mean axial velocity, this is CA3, and outlet mean absolute velocity angle theta 3, that is theta 3. Outlet mean absolute angle velocity with respect to axial is shown as theta 3, which is shown as how much is angle made by absolute velocity with respect to axial direction. So this is a combined velocity triangle. This is inlet and outlet velocity triangle. You can separate it. This is inlet velocity triangle and this is shown here is outlet velocity triangle. So this is all about inlet and outlet velocity triangle of Pelton wheel turbine. So I hope you enjoy this. Thank you. Thank you for watching.